Hello, I'm Nadia Daoudi. I'm a doctoral researcher at SMT at the University of Luxembourg, and I will present our work, DexRay, a simple yet effective deep learning approach to Android malware detection based on image representation of bytecode. This work has been conducted together with my colleagues Samhi, Abdoul, Kader, Kabore, Allix, Tegawendé, Bissyandé, and Jacques Klein at Jacques group. So I will start my presentation with the motivation behind our work. Then I will describe our approach, basic building blocks. After that, I will present our study design and our results. So as you might know, deep learning networks have achieved impressive results in several domains. Given a set of images that include cats, for example, the deep learning network can easily recognize if a new image includes a cat or not. Inspired by this idea, we aim to predict if an Android APK is malware or benign based on its image representation. Usually, researchers extract the features manually from the Android APKs. However, with image-based Android malware detection, the features are extracted automatically during the training. We propose our approach, DexRay, which is an image-based Android malware detector that relies on a simple image representation of the apps and a straightforward deep learning architecture. I will now present our approach basic building blocks. So we have two main steps: the image representation of the apps, which consists of generating the image from the APK file. And then we have the deep learning architecture, which consists of training the deep learning network using the images we generate with our approach in order to predict if a new Android APK is malware or benign. Obviously, the deep learning model needs to be already trained using images of Android APKs. So now I will present each of the previous steps in more detail. So for the first step, we extract the Dalbec bytecode from the APK file. Then we vectorize it, and we map each byte in the Dalbec bytecode to a pixel value in the image. We have opted for a vector image representation in order to not distort the sequence of the bytecode from the text file. Unlike some related works that have opted for a square or a rectangular image representation of the apps, we believe that such representation is not appropriate for Android malware detection, because the sequence of the pixels in the square image depends on the theory of bytes in the Dalbec bytecode. And having such representation can result in having patterns that start at the end of a line from a square image and finish at the beginning of the next line. We have decided to keep our image representation as simple as possible by using a grayscale image representation. We have also resized our images to have a fixed width of 128 times 128, so they can be used by the deep learning model. Similarly, we have opted for a simple deep learning architecture. So we have used two one-dimensional convolutional layers and two max pooling layers for our feature learning unit. And we have used two dense layers for our classification unit. So we have as input a vector image. Then the feature learning unit extract or learn useful patterns from the vector image and generate feature maps. These feature maps are then passed to the classification unit that learn to distinguish benign from malware apps, and it can be then used to predict the class of a new Android APK using its image representation. In our study, we investigate four main research questions. The traditional question is related to the evaluation of the approach in the task of Android malware detection, which is our first research question. And as you might know, time consistency is a common pitfall in Android malware evaluation. In our study, we also evaluate DexRay in the task of detecting new Android malware. We have also investigated the impact of image resizing in the performance of DexRay with our third research question. And we also study the robustness of our approach to apps obfuscation in our fourth RQ. We have relied on a dataset of Android apps from Androzu, which contains apps from 2019 and 2020. And we have kept the apps that we were able to generate their images and also the apps that we were able to extract their features for dripping approach. Dripping approach is a malware detector that we use for our experimental comparison. In our study, we have designed our experiments as follows. We have split our dataset into 80% training, 10% validation, and 10% for the test. We have also repeated our experiments 10 times in order to ensure that our results do not depend on a specific split of the dataset. We have also relied on the early stopping during the training of the neural network in order to ensure that our model does not overfit the dataset. We also compare our results against 3 Android malware detectors. So the first Android malware detector is Ribbon, which is a static analysis-based classifier, and R2D2 and Ding et al. Approaches, which are both image-based malware detectors that rely on sophisticated image representations and deep learning models. For example, they use colored images and they use some advanced architectures such as Inception v3. We have conducted our experiments, and the first research question, we evaluate DexRay on the task of Android malware detection. And since the implementation of Ribbon's replication is publicly available, we have used it in our experiments. As for R2D2 and Ding et al. Approaches, their implementations are not available, so we rely directly on the performance metrics that are reported in their papers. As we can see, the detection performance of DexRay is high. Also, the simplicity of the design choice of DexRay enables to report a detection performance that is comparable with related approaches that rely on sophisticated design choices. In our second research question, we evaluate the performance of DexRay in detecting a new Android malware. So we trained DexRay using apps from 2019 and we tested using apps from 2020. As you can see, DexRay enables to report a detection performance that is high on new Android malware. And these results suggest that our approach is robust against time decay and it's able to generalize. And the third research question, we investigate the impact of image resizing on the performance of DexRay. So we have used the various values for the width of the images. And as you can see, when the width of the images is above 128 times 128, the performance of DexRay is stable. But when the width of the images is below 128 times 128, the detection performance of DexRay decreases. These results suggest that the optimal width of DexRay's images is 128 times 128. In our fourth research question, we studied the robustness of DexRay against apps obfuscation. So we train DexRay using non-obfuscated apps, and we test it on obfuscated apps. We have two data sets of tests. We have test one, which includes obfuscated apps that DexRay has seen their non-obfuscated version in the training. And we have also test two, which includes obfuscated apps that DexRay has not seen their non-obfuscated version in the training. And in both cases, we can see that the performance of DexRay is low. As for Dribin, its detection performance is stable. In our second experiment, we have used data augmentation. So we have obfuscated 25%, 50%, 75%, and 100% of the apps in the training. And we have tested DexRay on obfuscated apps and non-obfuscated apps. And as you can see, the performance of DexRay is now high. And even with a slight data augmentation of 25%, we can see that DexRay enables to report a high detection performance. In our work, we have studied the feasibility of leveraging a straightforward approach to malware detection that relies on a simple image representation of the apps and a straightforward deep learning architecture. Using a large dataset of Android apps, we have demonstrated that our approach is highly effective. We have also studied the impact of image resizing on the performance of DexRay, and we have demonstrated that DexRay is robust against time decay and against obfuscation. Our results suggest that image-based Android malware detection is indeed promising. We released DexRay's source code, the dataset of apps, and the dataset of images. And we expect our work to serve as a foundation baseline for further developing image-based Android malware detectors. That concludes my presentation. Thank you.